Good morning, everyone. Today we are here for the Lab 2 submission and peer evaluation. The project is to observe the motion of an object that is dropped from rest and falls somewhat slowly. We do that by capturing a video, putting into tracker, and then using the software to track the object's position and match it with the time. Concept involved is the Newton's second law of motion. As per the rubric, we don't really require any coding as can be seen here. However, two of the questions require close scripts. I've put in the code there. Please have a look at this video. This shows Newton's second law. An object can be seen falling down. The gravitational force causes the body to accelerate. So the Newton's second law is a quantitative description of the changes that a force can produce on motion of a body. It states that the time rate of change of momentum of a body is equal to both the magnitude and direction of to the force imposed on it. So this is the distance time graph. As can be seen from the video before, the object at rest is dropped and accelerates due to gravitational force, and the slope of this graph of this line is non-constant and non-zero, indicating an accelerating object. I have taken the brown scale that you can see in the video is all like 1.2 meters long as a calibration stick. In the experiment, a marker can be seen being dropped. It is a one-dimensional system where the trajectory of the object is taken as the y-axis. The object moves in the negative y-axis. These are the initial conditions. You can see this is 1.2 meters, and the object starting position is 1.214 meters. The initial velocity obviously is zero. Because the object is falling down and it's on a negative y-axis, the object moves towards the negative y-axis with a non-constant negative velocity. So it will have a negative velocity due to the effect of gravity. The distance time table from the tracker. These are the all three graphs put together. The experiment, the one with drag, and the one without drag. Right. So the one with experiment is in the blue, where we can see that there's a little bit of variation, but it more or less converges with the one without drag. However, the one with drag, eventually what happens is that when the air resistance is when the drag is equal to the gravitational force, the slope becomes constant, as can be seen here. This is the code beside it. Let's go on to the what does it mean question. It has what is terminal velocity. The objects falling through air experience a drag that prevents them from speeding too quickly. Eventually, the drag will balance the downward pull due to gravity, resulting in no speeding. Thus, the object has a very constant velocity. Thus, the net force on the object when it reaches the terminal velocity is zero. Which answers this question. These are just the Desmos graph of the same thing we saw here. And the what if question is the question basically asks if there's force on the object while throwing it down, will it change the terminal velocity? The answer is no, the terminal velocity is same, because the drag is directly proportional to the square of velocity. As the if the velocity is greater, the force of the drag also will exert a much greater force, which will result in it achieving the same terminal velocity. So in this graph, an object is thrown without any force, and so it teaches terminal velocity this through glow script. And when the object is thrown through immense force, so I've considered that due to it being thrown by very immense force, it has a very high velocity. However, due to drag, it again comes down and it becomes constant. So the terminal velocity is same for the same object in both the cases. This is the formula for the drag, which I've used in the three graphs thing before. Yeah, errors may have occurred, like the air resistance. There may be also the calibration error, because I've used like the Apple Measure app to measure the Brown scale, which is used as a length of reference. What is in the predicted when drag was not considered. However, in reality, drag is always there until unless we are in a vacuum. In my predictions, the object falls perfectly perpendicular, but in reality, the object could have fallen at slight angle. There may be measurement errors and calibration errors. However, as can be seen from the graphs before, we get more or less the same results. This is the solution. Please pause the video to see it. These are the final results. We drop the object from 1.21 meters. In 0.5 seconds, it comes to 0.0 meters. So the total displacement is negative 121.4 centimeters. and the velocity is negative 4.9 meters per second, and we get the acceleration due to gravity as 9.8 meters per second square. Thank you so much. Have a nice day.